Maybe we can start. So the time is up. So hello everyone. Today we will discuss another paper about the VIT. This one is more like a follow-up paper of the VIT paper. The title is called Swin Transformer. And presented today will be Naveen Kanuri. And Naveen will share with us about the ideas he has. I mean, then he will also need a discussion with us for this paper as well. Yeah, so I can give the time to the presenter. Naveen, you can start when you are ready.
Yeah, thank you, Professor. So, hi everyone. My name is Naveen. So today we'll be talking about the paper Swin Transformer, Hierarchical Vision Transformer using shifted windows by Liu et al. They are members of Microsoft Research Asia. Let's begin the presentation now. So previously in this class, we discussed what transformers are, what is self-attention in the transformers architecture, and how they beat LSTMs in natural language processing, etc. And last week we discussed vision transformers and their robustness. There will be a kind of recap here. So let me walk you through the memory lane to refresh these concepts again briefly. This is particularly important for our paper as well to set the background as we get to understand how the idea of Swin Transformer came about. So like what are transformers? Like we know, we all saw this architecture, model architecture. So this is transformer architecture block. So this is an encoder, this is a decoder. So the core part of this architecture is self-attention layer, which is here. So the question is with this architecture of transformers, like how did transformers beat LSTMs in natural language processing? So for that, we'll take a quick look at the drawbacks of LSTMs in the first place. LSTMs were first slow to train. Like recurrent neural networks are already slower to train because we need to provide data sequentially while training instead of parallelly. A hidden state would require inputs from all the previous words to make any progress. So this kind of architecture doesn't take advantage of today's GPUs and massive parallel processing because GPUs are optimized for like parallel processing. And coupled with the added complexity in an LSTM in the form of multiple gates, etc., like LSTMs are even slower to train compared to RNNs. And the second weakness is low contextual awareness. Normal LSTMs process the words in a single direction, in one direction, maybe left to right. And this limits the contextual awareness of the network. Even the bidirectional LSTMs, which learn the context in both forward and backward direction and concatenate them, a better approach would be to look at both sides together at the same time. And the third drawback of LSTMs is they're very bad at long sequences. We already know that LSTMs can perform better than RNNs due to the presence of gates. But even with this, the improvement in the case of LSTMs is not that significant when we are trying tasks that maybe like crunch a large number of sentences, for example, text summarization and maybe questions and answers, etc. So now that we have taken a look at some of the issues with LSTMs, we'll see how the transformers architecture elevates these problems. So in a nutshell, like first there is an encoder block, right, in a transformer. So an encoder tries to understand the context of an input sentence and in the process learns what the language is. Let's see how the data moves in an encoder. The input to an encoder is a sentence. These individual words are first tokenized and replaced by pre-trained word embeddings um, in the input embeddings layer. In the next step, we add a position encoding to individual word vectors, essentially a function that maps to the position of a word in a sentence. And to this, we add our initial input embeddings to make sure that apart from the word, we also have a position aspect of it embedded in while we pass the sentence into the encoder. So next we pass this to a self-attention layer. The idea here is to create a matrix of importance of each word while defining context of other words in the same sentence. So each word would obviously have significant importance with itself and then with other words. And finally, we pass it through a feed forward layer, which is basically a dense neural network layer. And the biggest advantage of this transformer network is that we don't need to pass the data sequentially, but we can pass the data in parallel. This like greatly improves the training time. And since we are looking at the words in an overall manner, like not in a particular sequence, one after the other, and that too without any directional sense, the overall understanding of the language or context is much better than other architectures. So here we can see an example of a sentence where attention is playing a role. So here we can see that the darker the red, the higher the attention each individual word has with all the other words. So we can clearly see that when processing the word the, so highest attention is paid to the most relevant word, that is dog, by the model. Similarly, when processing the word big, the model learns that the most relevant word here is dog. And similarly for other sentences too, or like for other words in the sentence too. Next, we will see what the decoder is. In a nutshell, the decoder takes the output sentence as input and tries to like output the next word. For example, in the case of language translation. So the first step is similar to encoder. Here, embedding coupled with positional encoding for each output word is the input to the decoder first. Next, we compute a masked self-attention. This is slightly different from before, as here we are intentionally masking the words that are yet to come. Essentially, we don't provide the words that are supposed to come next while calculating the importance of the current word. So, and then the input from the decoder network is looked at alongside encoder's input. And finally, as the word travels through the feed forward and linear layer, we reach the softmax. The softmax is essentially on all the words in a vocabulary, which gives us a probability score for all the words in the dictionary for the next word. And the highest probability word is chosen for each portion, and this process happens in parallel. So now that we got an understanding about how, a brief understanding about how transformer works for natural language processing and overcomes the disadvantages of LSTMs, we can ask a question like, how do you take this concept and apply it to vision domain? The response is, the answer is the vision transformer from the paper image is worth 16 by 16 words that we discussed last week. So let's take a brief look at the vision transformers architecture. In the case of natural language processing, say for example, language translation task, we took a sentence, tokenized the words in that sentence, and gave them as input to a transformer's encoder. By doing this, the model learns the context of each word with respect to each other word in that sentence. But we can do the same thing with an image. Like it is infeasible to take each individual pixel and make the model learn the context of that particular pixel with respect to each other pixel in an image. Like it's a like quadratic computation complexity will arise. Because even for a small image size of 256 by 256 pixels, it will lead to 256 squared number of computations. And the other important thing is each pixel by itself doesn't carry enough meaning. Even to us, like it's a group of pixels that make sense. Um, and each individual pixel doesn't make any sense by itself. So the others in this vision transformer paper divided each image into a set of patches. Here, they have divided them into 16 by 16 patches and input these patches into the encoder, transformers encoder, after adding their patch and positional embedding information here as an input to the transformer encoder for classification task. So let's look at like performance of vision transformer. Like vision transformer achieved impressive results in image classification despite having less inductive bias compared to convolutional neural networks. We know that convolutional neural networks are tailor-made for vision tasks, but in the VIT paper, the only inductive bias we are giving to the transformer is that we divided input image into some fixed number of patches. As we know that unlike natural language processing, calculating each pixel's content, like each pixel's context to each other pixel in the input image is infeasible and not worth the computation actually. Even with this low inductive bias, vision transformer managed to achieve impressive accuracy in the image classification task. And the other paper we looked at last week was understanding the robustness of vision transformer to various changes like input perturbations and model perturbations. We know from, like we studied from the paper's results that VIT model has good robustness against these perturbations and is not in any way inferior to convolutional neural networks. And we also studied one paper like attention is all you need, not all you need actually, before I think the previous week. And they studied, they mentioned that self-attention possesses a strong inductive bias towards token uniformity. But with the presence of skip connections and multi-layer perceptrons, they stop for the output from degenerating exponentially to a rank one matrix. So in summary, so far, from what we studied so far, we got to know, like we understood that vision transformers are good and maybe even better than convolutional neural networks at image classification task, and they are robust to perturbations. So is VIT the holy grail? Is VIT all we need? VITs are very good at image classification. We have seen that last week. Then what about other vision tasks such as semantic segmentation and object detection, etc.? For example, say, is the VIT model good enough to perform at par or even beat CNNs in these tasks? Yet to know. And what about the patch size? What is so like sacrosanct about the number 16 or 14? Like from what we saw last week, it's tied to the image size, right? So So what happens when we vary the patch size? And what happens if we vary the input image size? From what we saw last week, if the image input image size increases, and if we keep the number of patches constant, then the more number of pixels or more information will go into the same patch, right? Similarly, if image size decreases and if we like keep the same number of patches, it will result in each patch not containing that many pixels or not containing that much information. Right. So similarly, we can argue by varying the patch size like 16, 14, or 32. So, but these are all like hyperparameters, right? But then how do these are the questions like will come, like what happens if we increase the resolution of input image or number of patches, etc. But how do we how do convolutional neural networks deal with these problems? Like these problems are common in both tasks, right? Like the same when even if we our model is transformer or our model is convolutional neural network, right? So like before asking ourselves this question, like let me describe briefly, like take a detour to describe other vision tasks besides classification that is this particular art paper, like Swin Transformer paper talks about. So, sorry. So the first one is semantic segmentation. Sorry for that. Image segmentation is a computer vision task in which we label specific regions of an image according to what's being shown. Like here, given this image, we have to predict that this is a person, like these pixels belong to a person, and these pixels belong to a bicycle, and these pixels belong to background. So we are trying to find answers to the question like what's in this image and where in the image is it located. Specifically, the goal of semantic image segmentation is to label each pixel of an image with a corresponding class of what is being represented. Because we are predicting for each pixel in the image, this task is like commonly referred to as dense prediction. One important thing to note is that we are not separating instances of the same class. Like the pixel here belongs to a different person, and this the pixel here belongs to a different person. But we are not trying to differentiate between two persons because they belong. This pixel and this pixel belongs to same class, a person. So here we only care about the category of each pixel. So if we have two objects of the same category in our input image, the segmentation map does not inherently distinguish these as separate objects. For that, there exists a different class of models known as instance segmentation models, which do distinguish between separate objects of the same class, but here as semantic segmentation doesn't differentiate that. So they are useful for tasks such as autonomous vehicles. We need to equip cars with the necessary perception to understand that their environment. And for that, the task is to differentiate a car. Like all cars can be categorized as the same class of cars, and there is no like advantage in distinguishing a car of type of a type, some say BMW and a car of type say a Benz or something like that. So and another like category where semantic segmentation helps is like medical image diagnostics. Machines can augment analysis performed by radiologists, greatly reducing time required to run diagnostic tests. I don't know why the images are not showing up, but we can say, for example, in a chest X-ray, we can differentiate pixels belonging to heart and pixels belonging to lungs and clavicles, etc., into various segments. So this is about semantic segmentation, and let's take a look at object detection next. So image classification here involves assigning class label to an image, where each object localization involves drawing a bounding box like this around one or more objects in an image. So object detection is more challenging and combines the two tasks, like drawing a bounding box around each object of interest in the image and assigning them to a class label. So together, like these two problems can be referred to as object recognition as well. And for these tasks, like region-based convolutional neural networks or RCNNs and their family of techniques are actually a state of the art before this paper, like before transformers. And they are designed for like model performance RCNNs, and there are another set of models called YOLO, you only look once. It's a second family of techniques for object recognition. They are more designed towards speed and real-time use. So what are the challenges faced by Vision Transformer to achieve good results, or maybe beat convolutional neural networks on these tasks? Let's look at some of them. So the feature maps produced by Vision Transformer are of a single low resolution because every patch is of the same size. And this won't work if we are doing dense prediction, like like when you are trying to classify at a pixel level whether that pixel belongs to a class person or a class bicycle. So this is one of the like drawbacks, if I may say, about Vision Transformer. And the other is we can't to achieve dense prediction like CNNs, we can't increase the number of patches to understand the image better at a smaller scale. This won't work because of the quadratic complexity. Because this involves computation of self-attention globally. Like, each patch's context is measured with respect to each other patch available at a global level, right? So to answer these, like answering these two questions is the basis of Swin Transformer. We'll see how Swin Transformer solves these problems, but before that, we'll try to like we can take inspiration from convolutional neural networks to understand how CNNs solve these problems before before taking the concepts and applying them to Vision Transformer. So CNNs have been the backbone for vision tasks, before the advent of transformers. CNNs have been most widely used not only for image classification, but also segmentation, object detection, style transfer, pose estimation, image synthesis, and other tasks as well. So what is the fundamental concept here that CNN has that made it so successful at all these tasks, not only at classification, but also others? So they extract features from the input image into a dense vector representation, And the density of this representation like increases as we go along the depth of the model. And they use these extracted features to solve the task at hand. So what do you mean by that? So let's take an example to understand this more clearly. So this is this is the architecture of VGGNet based on CNNs. So the first thing we can observe is that features of input image are extracted in a hierarchical manner. Like first, they are taken as 224 and 224 and 2 by 64. And then as you progress along the depth of the architecture, though the height and width of the representation at a particular level is decreasing, the width of the representation, it becomes dense. So this plays a key role in our Swin Transformer too, as we'll see in the coming slides. So here at first the depth is 3, then it became 64, then 128, then 256 and 512 and so on. So the second one that is like not shown in this picture is there is a concept of sliding window or a kernel that slides along the input in each layer to extract the feature representation for the next layers. So can we take these two concepts, like increasing the feature density as we go along the model step, and then use some kind of sliding mechanism or shifting mechanism, like Swin Transformer uses shifting. So can we take these concepts from CNNs and apply them to the Vision Transformer to make it better at other computer vision tasks too? And the answer is yes, we can. And this is what is being shown in Swin Transformer model in the paper by the authors. And here is a picture of that. And as we can see, the Swin Transformer model is hierarchical in nature. So on a high level, we can say that the input image is divided into some number of non-overlapping windows, and self-attention is calculated only in each window. And at every next stage, these patches get merged. Like if we compare it to vanilla Vision Transformer, like there is no hierarchical nature in this. So let's take a look at Swin Transformer's architecture. So this is the core part of the paper, which describes like how this model works. So with incoming input image of size this H cross W cross 3, the input image, we flatten this image, like we divide this into patches, say of a size 4 by 4 pixels each, and we flatten these 4 by 4 pixels into one vector. And the non-overlapping patches of size 4 by 4, where each pixel has 3 values for RGB, each patch will be converted to a vector with length 4 by 4 by 3, that is 48. And this vector will go through a linear embedding layer here. This vector will go through a linear embedding layer and gets converted to have a dimension C. So, and this goes through a modified transformer block called Swin Transformer block that I will show in the next slide. And this has some modifications. After this, we still get a feature map where each element has a dimension C. And the transformer and the linear embedding layer in front of it is called stage 1. And from this point on, the feature maps go through several repetitions of patch merging and then Swin Transformer blocks. And this procedure will be called a stage. Like patch merging is grouping 2 by 2 adjacent patches by concatenating the 4 elements and then applying a linear layer. For example, the first patch merging, since the input feature maps, each portion has a vector size of C, concatenating 2 by 2 patches into one will give a vector of length 4C. The linear layer following it will change the channel size from 4C to 2C again here. And this process acts as tone sampling, resulting the width and height of like feature map also get reduced by 2. And after patch merging, Swin Transformer block is applied. As we can see, like patch merging and Swin Transformer block application will, at each level gets the reduced patch size and then increased increased feature representation C2 to C to 4C to 8C as we go along the model's architecture. And this is repeated 3 times, and we get 4 feature maps from different scales. And this is the backbone structure which can be supplied to object detection, image classification, or semantic segmentation. So we'll see what Swin Transformer block is and what is so special about the Swin Transformer. There are 2 blocks in the Swin Transformer block. 2 successive Swin Transformer blocks, and the difference is here. One is where self-attention is calculated. One is window MSA, and the other is shifted window MSA. And there are 3 ideas here which are at the core. One is to split the patches into windows and then apply attention only within the patches inside each window. This will result, this will restrict the transformer complexity from increasing with respect to each feature maps patch size and the total number of window size. So, and the second one is after slicing patches into windows and applying transformers at the first time, the window splitting will be shifted and then transformer will be applied again. Like here, after shifting another transformer, like this block will be applied again. This allows, the advantage here is this allows adjacent windows to interact with each other. And then as you go along the depth of the architecture, like each patch will learn to learn the context of itself. And then even though attention is only calculated at a level, at a stage, attention, though it is calculated at in a single window, eventually every patch or every pixel will get will learn its context, will learn its global context as well. And then the third important thing is, while calculating attention, they've added relative position bias. We'll see what these exactly are. So first we'll talk about shifted window partitioning. So what is this? At layer L, if we have like 4 patches, and after shifting, this will become like this, like a patch will be taken from here, like here. And then this will result in increased number of patches, and then patches will become of different sizes as well. We know that there is a concept called sliding window in convolutional neural networks, where a kernel slides along the image and convolution operation is performed right. So, but here a simple window based self-attention module, like it lacks connections across windows. Like when attention is calculated in this window, with respect, each patch will learn its context with respect to other patches in this window only. So to introduce cross window connections while maintaining efficient computation of non-overlapping windows, the paper proposes a shifted window concept, like partitioning approach, like which alternates between two partitioning configurations in a consecutive spin transformer blocks. So here in the layer L left, so here in this left layer L, sorry, a regular window partitioning scheme is adopted, and self-attention is computed within each window. But in the next layer, layer L+1, the window partitioning is shifted, resulting in new windows. So here, the main reason for doing this is so that self computation in the new window crosses the boundaries of previous window layer in layer L. Providing connections among each window. So this shifted window partitioning approach introduces connections between neighboring non-overlapping windows in the previous layer. This is found effective based on experiments done in the Swin Transformer block. Like they have tried sliding window as well, but they came to the conclusion based on their experiment results that shifting windows is more effective. But we can clearly see that there is an issue here, because in layer L there are 4 windows, and here there have 9. So clearly there is a problem here. Let's see how the others overcome this problem. So since they do something called cyclic shift to merge some of these windows to make them of same size as the previous layer. A naive solution is to pad the windows to a size like here. The size of this window is only 4x4 in this example, and here it is sorry, it's 2x2, and it's say 4x2, and it's 4x4. A naive solution is to pad the smaller windows to a fixed size, say 4x4 in this case, and mask out the padded values when computing attention. But this results in increase in number of windows, right? So if we do that padding thing, in the first layer, we have only 4 windows. Now we have 9 windows, resulting in increased computation of 2.25 times. So the others proposed a more efficient batch computation approach by cyclic shifting. Like here also they have 4 windows, but what they've done is they've shifted some of these patches from, say, the A 2x2 patch comes here, and C will be cyclically shifted here. Like B will come here, A will come here, and C will come here, so that the total number of windows remain the same, 4 windows. And so after this shift, but we have to calculate attention, right? So for this, there is no need of masking anything because it's the same. But here, these patches come from different, these belong here, and this B comes from here. So while doing self-attention computation, they mask these patches. So for computing, say for example, this patch, like they're masking these patches, and for this for calculating self-attention in this window, they don't need to mask here. So, and then they're doing reverse cyclic shift to get back the original position of the windows. So another thing they have added is relative position bias. We know from the self-attention paper that this is how attention is calculated, but here in this Swin Transformer paper, they have added this term B. This is to introduce relative position information to the key query product, query key product before applying softmax to calculate the value matrix weights for the query. So when an M by M window exists for a feature map, the relative position value either for X or Y axis will be somewhere in the range minus m plus 1 to m plus 1, right? So to integrate this relative position information, the others prepared a learnable parameter matrix called B hat with shape 2m minus 1 and 2m minus 1. And each element will represent a vector that represents relative xy position differences. And the actual relative position bias matrix B here, that will be sampled from the B hat, which I just mentioned. And through experiments, they found out that without any bias or without like using absolute position embedding gave the Swin transformer as an inferior performance. That's why they've added the relative position bias in when calculating attention. And the paper creates a few variants of Swin transformer: Swin tiny, Swin small, Swin like base, and Swin large. So sorry, Swin big and Swin large. And the model size is compatible to a vision transformer or data efficient transformer model, or ResNet 50 and ResNet 101. So the model sizes are controlled by the size C here. That is initial feature maps channel size. And they start with 96, and as the density of the Swin transformer increases, they increase the channel size as well. And let's study some of the results of the Swin transformer. And so compared to previous state-of-art transformer-based architecture, that is data efficient transformers, Swin transformers noticeably surpass the counterpart architectures with similar complexities. Compared with state-of-art ComNets, that is ResNet 8G16, etc. The Swin transformer achieves better better accuracy here, as we can see. And even compared to vanilla vision transformer also, they achieve improved accuracy. So these are the results that are done on regular ImageNet 1K trained models, and these results are obtained from by doing ImageNet 22K pre-trained models. So we can see the comparison of the number of parameters as well. So for example, in the pre-trained model, we can see that compared to bit large, that is vanilla transformer with 16 pass size, we can see that the number of parameters are less. And even they even consumed less number of flops, but achieved a similar accuracy on ImageNet. So, the next experiment, this is on object detection, that is COCO object detection dataset. And here also we can see that Swin transformer achieves significantly improved accuracy compared to ResNet 50 and across this various compared to various other models. And here also Swin large actually has got achieved better accuracy in this test also, in system level comparison also. And the third experiment they've done is on semantic segmentation on ADE 20K dataset. We can see that the model Swin large gets an improved accuracy score, that is MIOU score on when compared to data efficient transformer. Like we can see it's compared to 44, it is 53.5, but at the same time the model parameters is also 52. Here we can see that it's obviously around 4 times, more than 4 times more, and significantly has got more flops also, took more time to train. So the others also have done some ablation studies, like without shifting and shifting with shifting windows, and without including any relative position bias, as we have seen in that equation I mentioned in the previous slides. And they found that with shifted windows gave better accuracy results on ImageNet classification, and this is for object detection, and this is for semantic segmentation, and across the board shifted windows gave better accuracy, and then using relative position gave better accuracy instead of using no relative position at all across all tests and all data sets. And then they've conducted another ablation study on the sliding window model also, and sliding window kernel also, and they have reported the training time taken and the FPS achieved. As we can see, like the latency significantly decreases when compared to using sliding window model here. Whereas here it is in the order of 130, and here it is in 3 and 1.9. It's very less compared to using these other methods. And finally, they've conducted ablation studies on sliding window and shifted window. This is accuracy. Previous one is time taken, latency here, and this is the accuracy. And they've measured that shifted window accuracy is more like comparable to sliding window, but since it has less latency, this model is preferred here in this paper. So finally, we have seen in this Swin Transformer how it produces a hierarchical feature representation, like taking inspiration from convolutional neural networks, and it has achieved linear computational complexity with respect to image size, because the number of we are calculating self-attention only in a particular window, not on global scale. And we have seen from the experiment results and ablation studies that the Swin Transformer achieved state-of-art performance on COCO object detection and 80-20K semantic segmentation as well, when besides image classification task. So that's it for my presentation. If you have any questions, please go ahead.
Okay, any questions?
Hi, so I have a question about like this performance on NLP task. So I don't think like it shows. So I'm speculating like how would you speculate like this transformer would be performed? Like how's performance of it on the neural language processing? So I feel like it's like optimized for CV tasks. So I wonder, like, do you have any inspiration on how you might be working in NLP tasks?
As far as I know, transformers have already achieved a state of art on NLP. We can see from the results of BERT, GPT, like BERT models, GPT 2, 3 models. They're like very good at even giving displaying jokes as well. And we already saw, like in the first week, right, how they've like even writing code, learning how to write code in difficult languages like C++ as well, which is like heavy, syntax heavy. So I think transformer models like have defeated, I can say confidently that they've defeated LSTMs, and they're here to stay in NLP. And like the only thing that that is progressing in my view is in NLP is like increasing the parameter size and complexity of the model. Recently there is a paper by Google Research. I think there is it's a pathways model or something like that, which has like 640 billion parameters like in their model, and they've trained entire internet, entire GitHub pages and everything they've trained, and it's like the complexity increases, they are saying that their transformer model based NLP models are like able to generalize the tasks as well. We'll see. I think right now we are going through deep. We have covered deep learning, and then this week I think we'll be completing images, and in the coming weeks I think we'll see exactly like with results like where transformers stand in natural language processing domain.
Oh, thank you so much.
Yeah. Any other questions?
Okay, any more questions? We have been discussing 3 papers on VIT already. I hope you are not get bored, by these papers. So we have 3 papers in the sequence. Right? Any more questions from students?
Can you tell about the ablation study once more?
Okay, this one?
Yeah. So here they only used to study with the Swin transformer, right?
Yeah, Swin transformer. They've compared to the performer that this is also like this achieved previous to the Swin transformer. Performer achieved state of art in ImageNet classification tasks. So that's why they're comparing Swin transformer with performer here. This is also based on the transformer architecture.
But object detection, they haven't yet compared it.
Yes, yes.
Okay.
So this is comparing only accuracy. So if we compare accuracy, shifted window is like almost similar to sliding window. But if we compare, if we study this ablation study, sliding window is significantly slower compared to shifting window. When the results are like coming in 3 milliseconds and 1 millisecond here, they're taking like 122 milliseconds. So even though accuracy is similar, this model is inferior because of the latency present.
Oh, so that's why they say shifted window would be the best one.
Yes.
Okay.
So, any other questions?
Okay, so if there is no other questions, then probably that's it for today. Thank you so much, Naveen. For the talk is very good. And so for students, also a reminder for you, we have finished grading the proposal already. I think next you can move to the implementation of your paper, and for the project. And you don't need to wait until the end of this quarter to start work on your project. And you can start earlier, then you can have more time to polish your paper. Then you can have a beta version to be submitted to the system for this course in this quarter. So start earlier will give you more time to work on the project, right? So if you have any question or need to have any meeting now with me, you can let me know. We can have the office hour after today's class. And if you have any ideas to share with me, you can also talk with me as well. Okay, so let's thank the speaker. Thank you so much, Naveen.
Thank you, Professor. Thank you, everyone.
Okay, thanks.